Have you ever just stopped to think about how everything around us is connected? I mean, everything. From the sunlight that's warming your face right now, to the grass in a field, all the way up to the biggest predators in the world. It's all part of one giant, incredible system.
Yeah, I know. That sounds more like a riddle than a science question, right? But it's a real question, and it gets to the heart of it all. How does energy, the fuel for all life, actually move through our world? We're going to follow that exact journey, from a single sunbeam all the way to the king of the savannah.
All right, to answer that big question, we first need to get our heads around the stage where this whole drama plays out. So let's talk about the ecosystem.
The key word here, you really got to latch onto this, is interaction. See, an ecosystem isn't just a list of all the plants and animals that live somewhere. It's about how all the living things, the plants, the animals, and the non-living things, like water, soil, and sunlight, are all constantly mixing it up, constantly affecting each other. It's a dynamic, living web.
You know, this slide actually answers a question I bet a lot of us have had. Why do you have to constantly clean a fish tank, but a natural pond seems to just take care of itself? Well, your aquarium is an artificial ecosystem. It doesn't have a big enough cleanup crew, the decomposers, to break down all the waste. A natural pond, on the other hand, it's got that whole self-cleaning system built right in. Pretty cool.
So let's just boil this down into two big buckets. You've got the biotic components, that's all the living stuff. Everything from bacteria you can't even see, all the way up to lions. And then you've got the abiotic components, the non-living stuff that makes it all happen. We're talking temperature, soil, and of course, the sunlight that kicks this whole party off. Okay, so we've met the players on the fields. Now let's get into the rules of the game. Specifically, how does that initial spark of energy from the sun actually get passed through the system to power everything else?
This is the energy highway, and we call it the food chain. It all starts with the producers, plants, doing their magic, turning sunlight into food. Then they get eaten by the primary consumers, the herbivores. Those guys get eaten by the secondary consumers, and so on up the ladder. Each of these steps is what we call a trophic level. And as we're about to find out, something really important happens at every single jump.
Seems pretty straightforward, doesn't it? Energy just gets passed up the chain. But here's the twist. And it's a huge one. This is the thing that governs pretty much all of life on Earth. The energy transfer isn't perfect. It's not even close. Just let that sink in for a second. 1%. Of all the solar energy that hits a plant, only a tiny 1% actually gets turned into food. So before the food chain even gets started, 99% of the potential energy is already gone. It's just a wildly inefficient process right from the get-go. And that inefficiency just keeps on going up the chain. This is a fundamental law of ecology, and it's called the 10% rule. Basically, it means that every time something gets eaten, only about 10% of the energy from its body gets stored in the predator. Only 10% moves on.
So you gotta be asking, okay, where in the world does the other 90% go? Well, it doesn't just disappear. It's used for living. Every breath, every movement, every single heartbeat, that all burns energy. And that energy is released as heat. That 90% is basically the cost of staying alive. And this right here is the direct result of that 10% rule. It's the reason food chains are so short. By the time that energy gets from the plants to the gazelle to the lion, there's just not enough gas left in the tank to support another level of predator on top of that. The energy pyramid just runs out of steam. But hold on, there's a really disturbing flip side to this energy pyramid. While energy decreases as you go up, some really nasty stuff does the exact opposite. Things like pesticides. They don't get burned for energy. They get stored in fat, so they get more and more concentrated at every level. That's called biological magnification, and it means the animal at the very top, which is often us, ends up with the highest, most toxic dose. Which, of course, brings us to our own role in all this. Because, while we understand the rules of the ecosystem, our own activities are often throwing a massive wrench into that natural engine. But let's start with a really hopeful story, a true success. A lot of us remember the panic in the 80s about the hole in the ozone layer, right? It was caused by these chemicals called CFCs. But the amazing part is what happened next. The entire world came together, signed something called the Montreal Protocol to ban these chemicals, and get this. It worked. The ozone layer is actually healing. It's just this powerful reminder that we can solve the environmental problems we create.
But then we've got the challenges we haven't solved yet, like our garbage problem.
The whole issue really comes down to a simple biological question. Does the planet's cleanup crew have the right tools, the right enzymes to break something down? For an apple core, you bet. They've got the tools. For a plastic bottle? Nope, they just don't. And so that bottle just sits there for hundreds of years.
And finding a good solution here is so much harder than it looks. Even when we try to do the right thing, it can backfire. Take, for example, switching from disposable plastic cups to old-school clay cups. Sounds great, right? Eco-friendly. But then you realize that making all those clay cups could mean stripping away tons of valuable topsoil. It just proves there are no easy answers. Every single choice has a trade-off.
And so that brings us full circle. We've tracked this incredible, mind-bogglingly inefficient journey of energy from a sunbeam to a lion. And we've seen solid proof in the story of the ozone layer that when we decide to act together, we can actually solve these massive global crises. So the final question, the one I want to leave you with, is a tough one. Can we take that same global teamwork, that same ingenuity, and finally solve the massive waste crisis that we're all facing right now?